We saw in a previous video that topological sorting for a directed acyclic graph is a linear ordering of vertices v1, v2 to vn such that for every edge directed from vertex vi to vj, vi will come first before vj in the ordering. For more details, you can check my earlier video. So we had seen that for this given graph, the possible orderings are ABDCE or ABDEC. As we can see that for B has an incoming edge from A, that means A has to come first before B. We can see that A in this ordering, we can see that A has come before B. Now for B should be coming before C and D because there are outgoing edges from B to C and D. So as we can see, B has come before C and D in this ordering. Also we can see that D should come before C because there is an edge from D to C. Again we see that D is coming before C and D is coming before E as well. Same we can see in this case as well. Now we are going to see how we can use depth first search for finding out the topological sorting. So first of all, what is DFS and what is topological sorting? What is the difference between them? So in DFS, what we have to do is that we have to print a vertex and then recursively call DFS for its adjacent vertices or its neighbors. So if we have printed A, then we will keep on going into the depth till we have covered all its neighboring vertices and then we are going to backtrack. But in topological sorting, we need to print a vertex before its adjacent vertices. So if this is a graph, we can see that the DFS of this graph is one of the possible options is A, D, E, C, B. So we go from A to D, then to E, we backtrack and then we can go to C and then finally we can add B. So this is the DFS for this particular graph, one of the possible options. However, in topological sorting, vertex B should be printed before D because there is an outgoing edge from B to D. That means D has a dependency on vertex B. If we look at this depth first search, we see that vertex B is after vertex D. So it is not necessary that DFS in its current form will be leading to a topological sorting. So how we can use this? Let's take a look at the pseudocode. So this is the pseudocode of topological sort. So we will first have a stack which will be initialized to null and then we are going to create an array of visited. The size of this array would be equal to the number of vertices in the graph. Now what we are going to do is that we are going to visit or we are going to take a vertex which is unvisited in the vertex in the graph and we are going to call DFS on that vertex. When we call the DFS for that vertex, we are going to mark that vertex as true and then for all the unvisited neighbors of that vertex, now we will recursively call DFS. Once we are done with it, then we are going to push this vertex V onto the stack. If we have finished doing this for all the unvisited vertices in the graph, then once we have done that, then we are going to pop it out and add it to the list till our stack is empty. So this is the pseudocode and let's say how this is going to work for this example. So we have the stack over here and we have a visited array since the number of vertices in our graph is 7. So we are having these 7 elements. All of them have been initialized to false because none of these vertices are visited currently. So what we have to do now is to take one unvisited vertex. So this was our visited array. This I am showing A, B, C, D, E, F, G to tell you that this particular entry belongs to this particular vertex. So randomly I have chosen A. We can start with any other vertex. So we have chosen A. So we have to now call DFS on A. So when we call DFS on A, what we have to do is first mark it as visited. So now A has visited has been marked as true. Now when we go to call the DFS, we have to visit the unvisited neighbors of A. So we have two neighbors over here. One is B. If we see, there is an edge from A to B. So B is an unvisited neighbor of A and G is also an unvisited neighbor of A. So we can choose either of these. So let's say we have chosen B. So if we have chosen B, so that means now we have to call DFS on B and also mark B as visited. So we have marked B as visited now. Now there are two unvisited neighbors of B. We can go from B to C or we can go from B to G. So let's say we choose vertex C, and now since we are visiting C, so now we have to call a DFS on C and we mark C also as visited. Now we will see the unvisited neighbors of C. So this is a neighbor F and this is a neighbor E. We can choose either of them. So let's say we have chosen E now. So if we have chosen E, that means now we have to call DFS on E. When we call DFS on E, we also have to mark E as visited. And now when we check the neighbors of E, there are no neighbors. That means we have reached the end over here. So now we will push E, this vertex E, onto the stack. And now we will start our backtrack. So we backtrack from E to its parent, which was C. So we have gone back to C and now we explore other unvisited neighbors of C. So we see from C we can go to F. F is still unvisited, so we can visit F. So we go to F and that means now we have to call DFS on F. So F has been marked as visited. And now we check what are the unvisited neighbors of F. There are no unvisited neighbors of F. So F is also pushed onto the stack. And then we backtrack to its parent. So we backtrack to C and now from C we will see what are the unexplored neighbors of C. Now C has no unvisited neighbors. So that means this is a dead end for C also. So C is also pushed onto the stack and now we will go from C to its parent, which was B. So now we are backtracking to B and from B now we see what are the unvisited neighbors. We see that there is an unvisited neighbor from B, which is G. So that means from B we can go now to G. So we go to G, we mark G as visited because we are calling a DFS on G now. So from G now when we are calling DFS, we see what are the unvisited neighbors of G. But there are no unvisited neighbors from G. So that means we can push G onto the stack and then we have to backtrack. So we backtrack back to B and from B now we are checking the unvisited neighbors of B. There are no unvisited neighbors of B now. So we push it onto the stack and now we have to backtrack to its parent, which is A. So we go back to A and from A now we see what are the unvisited neighbors of A. Now we see that there are no unvisited neighbors of A as well. So we are done with A. So A is also pushed onto the stack. So what are the possibilities which are left now? So we now see that all the this depth has been explored now completely. So what are the other vertices that are left now, other unvisited vertices? Now we see that there is this vertex D which was left. So now we go to D, we call a DFS on D and now we have to mark it as visited also. and then we have to explore the neighbors, unvisited neighbors of D. When we see this is also explored, this is also explored, so that means there are no unvisited neighbors of D which are left. So we push D also onto the stack and we see that all our neighbors, all the nodes have been visited. Once all the nodes have been visited, we start popping the stack. So D goes out first, then goes A, then B, G, C, F and E. This ordering is not unique. Why is it not unique? Because when we started with A, we chose to go to B. We could have gone to G as well. If we had gone to G, our ordering would have been different. From B, we went to C. If we had gone to G, then also our ordering could have been different. That means at each node when we were making choices, we could have made different choices. That is why this ordering is not unique. Also, if you see over here randomly, we see that D and A, they are coming first because they had no dependencies. D did not have any dependency, A also did not have any dependency. Both had an in degree of 0. We see that D has to come before B and C because there are outgoing edges. So we can see in this ordering over here that D has come before B and before C. A has to come before B and before G. So we see in this ordering that A is definitely coming before B and G. B now, because there are outgoing edges to G and C, that means B has to come before G and C. That we can see over here in the ordering. C has to come before F and E. Yes, we see that C is coming before F and E. G has to come before F. Yes, G is coming before F. So we see over here that our topological sorting, all the edges have been taken care of and all the vertices which have dependency on other vertices, they have also come in the correct order. So the time complexity for this algorithm, if you see that this code, it is iterating through all the vertices in the input graph. So this is order of V time, and for each unvisited vertex, all the edges, in the worst case, all the neighbors of that vertex will be explored. That is, each edge would be explored. That would be a total of E work. So the time complexity for this algorithm would be order of V plus E.